the specific stuff you want to talk about just for like 2 minutes, because I'm going to break a little bit, because I think I don't know if there's going to be people learning about other venues that come in here.
No, nothing.
Okay. And maybe I'll just start writing on the board and we can just get going and they can catch up. Alright. So the first thing we're going to talk about was I just wanted to say, like, or maybe we'll work these bullet points, but we'll say, so this is going to be like, it's kind of up to you how seriously you want to take notes on this, but I just want to make 2 remarks on things we talked about last time that I think I did not emphasize them correctly, and so I'd like to just kind of clear that up. So the first one was we were talking about sort of these axioms that we've been dealing with, and I think I kind of repeatedly emphasized that we have like the well-ordering property of the natural numbers, and then we're talking about the real numbers. Something that's really special that happens is like we have the completeness axiom that we keep mentioning, which is about least upper bounds or greatest lower bounds, and then we have the Archimedean property, and you see we're using that all the time in sequences. And I think I kind of emphasized a bit too much these as just being like this collection of properties, but just one thing I want to say is that note that the completeness axiom implies the Archimedean property. Okay. So, you know, how much we'll use this in the course? Probably not so much, but it's just worth noting that this really is the kind of minimal assumption you need. You get this as a consequence of that. And I'll just give you a source for that if you want to see it. So that's page 19 of Abbott. Second edition. So yeah, if we were doing a course on like really rigorously constructing the real numbers, which is not our main focus right now, we could talk more about this. You know, do you need this? Could you get the implication this way? Like, what would you have to add on this side to say to get an equivalence and stuff like that? But we're not really going to focus on that. But I just wanted to emphasize that it's not this like long list of random axioms. We really just take this one and then we get this one as a consequence. But you see that we do use this one all the time. Okay, and then this was in our kind of our test review. This wasn't really something that went wrong, but I think it was something that I should have emphasized a bit more looking over the tests. So in test 1, question 1, okay, notice that the assumptions and I'm not going to spell out the whole question. You can go back and check our notes from last time, and you can check the memo for the test when it comes out. But the assumptions, we had a part in the proof where we had to assume that alpha squared was greater than 19, and alpha squared was less than 19. And what I want to say is that those assumptions were critical because we rearranged an inequality using these assumptions. Well, I'll say we rearranged an inequality from the Archimedean property I say this, we rearranged an Archimedean quality that we got from the Archimedean property is really what I'm saying. Maybe I should say when we rearranged an inequality. Sorry about this. I know you hate when lecturers or tutors do this, but here we are. We're critical when we rearranged an inequality from the Archimedean property. And this sounds kind of vague, and you may not know what I'm talking about, but if you just go back and look at either the test or look at the tutorial question, which had a very similar thing, where I think we were proving that the square root of 15 or something like that is a real number, you'll see there's a step in the proof where you had to assume this, and then you kind of show that there's a natural number that's bigger than some inequality, and then you rearrange that inequality to get this other set, chain of inequalities that you need. And it was really important that this was true. You needed to use that assumption because you kind of multiply by a denominator that might be positive or might be negative, and this assumption tells you that it's positive. And this assumption in the other case tells you that it's positive or whatever. If you go back and look, this will make sense. And the reason why I'm writing this is I just think that last week when we worked through question 1, I didn't emphasize this enough. We really didn't talk about that. We kind of just on the fly rearranged the inequality. We were like, oh, that's true, and then we got our answers. And this is actually quite important. The proof wouldn't have been true if we didn't have that assumption if we can use that assumption when we rearrange the inequality. And it was that inequality that we got from the Archimedean problem. Okay, yeah.
And then usually we're proving equality between those two numbers, and we have to, so we disprove those two to prove that.
Exactly, yeah. We also needed existence, right? So we said this alpha has to exist, y is completeness axiom, and then we could show that, well, if it exists, and this is false, and this is false, we know by the axioms that we've used for the real numbers, this ordering on the real numbers, then it has to be, you have to have equality, because that's the only thing left. All right, so that's kind of enough on last time, but that was just, I wanted to say those. All right, and then, so then I think our main thing is to move on and just kind of get going on series more. Who was here last time? I know you two, or you weren't here. How valuable is it for me to I kind of wrote up a list of our strategies for solving different types of series questions. So I said well, there's sort of two broad categories of questions that you'll see. The first is calculate the result of an infinite series. In other words, what is the literal real number that infinite series converges to or equals?
That was really useful.
Yeah. So we had like a list of 2 or 3 things that go with that. What should you check to do that? And then we said you could have another type of question that just says, does the series converge or diverge? It doesn't say find the result, but it says just does it diverge or converge? And then we had bullet point lists. Do you want me to write that again? Or do we have it in our notes and maybe you can check the recording? How do we feel about that?
I mean, I've got it down.
You've got it down? And you feel? Okay, so you can check the recording. Just to say it briefly, the broad idea was something like, you don't want to have this long list of things that are all floating around your head, and then you face a question, and you're like, oh, what do I do? It's much better if you can just say, oh, this is this type of question, and really the only tools that I have that'll give me that are, say, 1, 2, and 3, and then you just check which of those is appropriate for that question, right? So if they say, find the result of this series, calculate the number it converges to, you're never going to use the comparison test, so you don't ever even want to think about the comparison test, because the comparison test doesn't tell you the result of the series, it just tells you whether it converges or diverges, and so on. So you'll go and check, but broadly speaking, we had say 3 things you could do. You could check geometric series, telescoping, or you could try to prove the formula for the sequence of partial sums using induction, perhaps, and then you take the limit. But anyway, we can review that. All right, so perhaps what we should do is just jump into doing some problems then. So tutorial 6 is kind of a natural place to start. I think that, did we talk about question 1A last time, which was, you can just write it down, was something like this. 3k minus 1 and 3k plus 2, I think.
from tutorial 6.
Yeah, this was the very first.
Minus
These swap things. Did we talk about this last time? I actually don't remember. We didn't. Okay. So I think, and was K going from 1 or 0? 1. All right, so I'll just write this up. 6, question 1A. Okay. So I think we could probably most of you solved this already because you were at the tutorial and you figured it out, you got some help from tutors, but so we won't spend an enormous amount of time on it, but I think we should just check that some of the things on that list from last time can really be applied here. So I think you've seen this already because I talked to you about it. So sorry about that, but we'll go a little quickly. So first of all, the question said, I think it said check whether this diverges or converges, and if it converges, find the result. Okay. So how would we check that it converges? Well, I guess this is going to show up later in all the questions we're going to do, but we'll say, so general rule for checking converge / diverge of ratios of polynomials possibly involving roots. By that I mean it could have square roots in it. You'll see in 1b there's something with square roots. You'll see that later in the other question. Maybe it'll have cube root, maybe it'll have fourth root. So what's our general rule when we see this kind of ratio of polynomials? Because this is really a kind of a common problem. You want to estimate let's say the power, maybe power is the wrong word, how should we say this? If I say the order of the numerator, does that ring a bell? Is that kind of a familiar term? I would say the order of this numerator would be kind of 0, because it's k to the 0 power, and the order of the denominator would be kind of power 2, because the highest power of k is 2. If I say order like that, is that something familiar? Okay, so let's use the word order. I don't know if I want to say power, exponent, or order, but okay, let's say the order highest power of the variable of the numerator and denominator and then use the comparison test. So I'm writing out this long speech because we are truly going to kind of use this over and over again, so it's probably worth just writing out. Perhaps they mentioned this in lectures. Did they say something like that? Okay, so I'll kind of explain why that makes sense, but it will be intuitive. Sorry, I'm just looking for an eraser. I'm sure it's around here. Did I miss it? Oh, there it is. Okay, so basically the idea is when you're looking at this infinite series, you're really trying to add up this infinite list of numbers in some sense. And really the earlier numbers don't matter that much. We've kind of seen that. Like, I'm not sure exactly how to make that precise in the most convincing way, but do you agree with me that like if I have an infinite list of numbers and I just delete the first 10 numbers and then I add up the rest of the list and I find out it converges to some number, I can get the result of the first series by just adding those 10 numbers on, right? Like the study of infinite series in some sense is really just the study of the tails. It's like the study of how it behaves as you're adding up all these things to infinity. The first bit kind of doesn't matter. And when I say that, I really mean up to any finite number. So it doesn't have to be up to 2, it could be up to 10 million. If we can delete those first 10 million numbers and then the rest of the infinite list converges, we can add them back on or something like that. So to get a kind of intuitive sense of what's going on here, what really matters is when k is large. In some sense. It doesn't really matter what's happening when k is 1 or when k is 2 or when k is 3. If we want the exact answer, we need to care about that. But if we just want to check whether it converges or diverges, it doesn't really matter what's happening when k is small. We care about when k is large. And what does that mean? That kind of means, roughly speaking, or literally speaking, taking the value as k goes to infinity. And you'll notice that if you have a polynomial in the denominator, and this is also a polynomial in the numerator, it's a constant polynomial, the highest power of the variable is what matters as you go towards infinity. As k gets large, you see that this is a quadratic polynomial if I multiply this out. So the power 2, the k to the power 2 term, is the term that matters the most. Because k to the power 2 gets bigger much faster than k to the power 1. Okay? So the general idea that I'm trying to say is that the highest power of the variable in the denominator is what kind of determines how this whole object behaves as you go to infinity, and the highest power of the variable in the numerator also determines it, right? Those are the two things that matter the most. This is just sort of a rough understanding to guide you, but it really is true. So what we're saying here is estimate the order, the highest power of the variable of the numerator and the denominator. So we'll just say here, in 3 over 3k plus 1, 3k minus 2, numerator, so let's say this, we'll say something like this, the order, okay, or what's the order? The numerator has order 0, okay? Constant polynomial. We can think of the variable being to the power 0, okay? The denominator has order power 2. Okay, and we all sort of nodded our heads, so we believe that. Power 2. Why? Maybe for the people watching at home, it's a quadratic polynomial. Okay, so we multiply that out, and we have a quadratic polynomial. So then the overall order this is actually it. Really how I want to say this. Sorry, that's this is not how you handle ratios of variables, of course, with exponents. What we want to say is the overall order is 0 minus 2 equals minus 2, right? Okay, so what I'm doing is I'm sort of, let's just write i.e. k to the 0 over k to the 2 equals 1 over k to the 2. And this thing has order minus 2. Okay, that's what I was saying, sorry. For a second I was looking at it, it's like 0 over 2, that's not right. Excuse me, it's been a long back. It's been a short back, I don't know. What's the excuse? So maybe what I can do is put this up in the corner so don't start writing. So just to remember, the problem we're working on is this, up to infinity, k equals 1 over 3k plus 1, k 3k minus 2. All right. Okay. So what does this teach us? Knowing the overall order as k gets large, knowing how this kind of this fraction kind of behaves as k gets large. Look, you might want to put the constant in front too, if you want, if that guides you more clearly. But as you kind of take the limit as k gets large, oh sorry, let's not do that. We'll talk about that in a second. Is going to give you a guide of what you should do with the comparison test. Okay? So, knowing the order, overall order, as k goes to infinity, tells you how to use the comparison test. Okay. And just to be clear, remember the comparison test is for, we haven't really talked about this a lot, but the comparison test is for when all of the terms are adding up are positive. So everything on this tutorial are series where all of the terms are positive. We will talk about some series where the terms are allowed to be negative and positive in a bit, but we haven't really done that yet. So anytime I say this is guiding you to use the comparison test, we all agree that it's appropriate to use the comparison test on a problem where all of the terms are positive. These are all positive numbers, every single one of them. Okay, so tells you how to use the comparison test. So what does it tell you? It says the order, if it's less than minus 1, okay, likely converges. Okay. And you should use, okay, I'll write overall here, overall order. Less than 1 likely converges, greater than or equal to minus 1. Well, I don't even know if I need the word likely here. I think this is just a term, but anyway. When I do these problems, I just think of that we're working roughly. You know, we're just kind of trying to figure out what's probably true, and then we prove it. And so here we're going to say diverges, okay? And so really, in some sense, this is just the ratio test hidden, but you haven't discussed the ratio test in class. I think it's left as an exercise. Okay. So we will discuss that rigorously at some point. But this is just for the purpose of this tutorial. I want to show you that sort of intuitive notions about how polynomials work is more than enough to help us just use the comparison test and prove everything we need to do. So then you have an idea of whether it converges or diverges, but now you want to show it using the comparison test. So what do? And this all, what you're going to do is use some constant say, I'll just say b over k to the a, where b is some, sorry, this is probably not the right way to write it. Let's write it this way. B, k to the a, I apologize, is some constant, where b is some constant, and a is the overall order. Okay, so this is what you're going to use, okay? To compare. So this is sort of your general strategy. You're going to try to figure out how does the series behave as the variable gets large, whether that variable or index, as you think of it, as k or j or whatever index variable we use, or n. And as it gets large, it's going to kind of hint at you at its behavior. Is it, as it gets very large, is it starting to behave like a harmonic series? That would be when it's actually the overall order is -1. Is it something that's even bigger than the harmonic series? So then it's probably diverging even more. Do we agree that if the overall order was just 0, then it's kind of behaving like a constant? So if you're adding up a constant infinitely many times, it's going to diverge. If the overall order was k squared, that's definitely going to diverge as you go to infinity. You're just going to be adding up bigger and bigger numbers. So that's sort of the intuition behind this. And then this part where we say that it likely converges, and in fact does converge, the idea is kind of, again, relating to our p-series, that something smaller than the harmonic series, all those powers of k that are smaller than the harmonic series are going to converge. So if we have 1 over k squared, 1 over k cubed, 1 over k to the 3 over 2, those are all going to converge. And then what I'm saying here is this is the function we're going to compare with. Perhaps I wrote this down in a kind of convoluted way. If you want to, you can really think about it in terms of your p-series, so you have fewer things to remember. The idea is really this. But we'll see by some examples that what I'm saying is not really that fancy. And I just hope that you have a guide for when you go back to study for the test or exam. You really have it kind of written out why it works. Okay, so what should we do? We should use it for this problem. We figured out what the overall order was. And since it's -2, in other words, this thing is behaving like 1 over k squared, or some constant times 1 over k squared, as we go to infinity. When I say this thing, I mean that. We have an idea that it probably converges because it's kind of behaving smaller than the harmonic series, and all of those 1 over k to the power of p, all of these guys where p is greater than 1 are going to converge. And so then we also have a guide for what we should use for our comparison test. We said it should just be some constant times k to that overall order. So let's show that. Also, by the way, you may be wondering, why are we doing all this? Because I did the tutorial, I did 1A already, and I figured out what the formula was for S for the partial sums, and so I know the answer to this problem. Why are we writing this whole long thing? The point is, I'm just showing you, this is a general strategy that works for this, and for like everything else in the tutorial, okay? And this will also, once you internalize it, it just saves you time. Because you'll just look at the first problem, you'll be like, okay, that definitely converges, so now I need to find, I go to my list of things that I need to do. Is it a geometric series? Can I write down a formula for the partial sums, etc.? You'll be able to tell whether it converges or not within seconds. Or at least you'll have a hint that it probably does. Similarly, you might say, okay, wait, no, I'm pretty sure it diverges. So then you're not gonna, I mean, you might still go down through the process of saying, okay, let me find a formula for the partial sums, but you might not. You could find something easier, perhaps. Yeah. So that's why we're kind of going through all this, and then it will be used for the rest of the questions. Okay. So what was our overall order? It was -2. So my idea here is that I have 3 over 3k plus 1, 3k minus 2, to infinity, k equals 1, and I suspect that it converges, okay? And so what I'm looking for is something that's greater than or equal to it, okay? I want to find something bigger that converges, and then by the comparison test I know that this converges. Perhaps we won't write this. We really just deal with these terms. So I suspect that I need to find something bigger. So how do I do that? I need to make the denominator bigger. I mean, sorry, the numerator bigger, and I need to make the denominator smaller. That's how you find something bigger. Okay. So we should I write that out, or did that kind of make sense? But okay. So I'll just write here, make numerator bigger, denominator smaller. Okay? I'm looking for something that has a bigger numerator and a smaller denominator. Why? Because that thing will be bigger than this. Okay? So what's the thing I'm looking for? Well, what has a let's say it this way. So remember, my guide is also to, okay. So let's make the denominator bigger. Okay. So how can I make the denominator bigger? Did I lie? No, sorry, I'm getting a little lost. We're making the denominator smaller. Okay. We agree with that. So how can I make the denominator smaller? Okay. Any ideas? I could just throw away these constants. Okay, right? So if we just do that, remember this is some number, and so if I just don't have that constant, I have something smaller, and that'll make the overall thing bigger. So I would just have 3k, and then I could, okay, we're worrying a little because it's a minus sign. What we could do is we could make it a -3. Yeah, that would make it smaller. Do you agree? Perhaps I'm getting myself into a little trouble here. Okay, let's wait a second and see what we can do here. Notice that if you have 3 over 9k squared minus 3k minus 2, okay, we want to make this one smaller. Do you agree that this is less than or equal to 3 over 9k squared minus 3k squared minus 2k squared? Because these are negatives, so putting squareds there is going to make these things smaller. But the overall thing never gets negative, so we don't have to worry, because we're luckily, just for this expression, luckily 3 and 2 are not going to be bigger than 9. Okay, so that's quite a nice solution, I think. So you can just combine it all together and you have 4k squared, and that converges by p-series, right? If you really wanted to, you could even do this. But you know this, even if this constant is greater than 1, it still converges by p-series, right? So that's beautiful, I like that, well done. So yeah, that's kind of a general technique that'll get you out of problems when you have minus signs. That's much better, I should have had that ready. Okay, so, all right, so we went through this whole long thing, and we learned that this converges. So let's calculate its sum. That's the next thing that we're asked to do. We're asked if it diverges, you know that. Otherwise, if it converges, calculate its sum. So finding the sum. Well, I think all of us were kind of advised towards partial fractions in the tutorial, right? Are we all cool that we could go that route? We could use partial fractions on this. Actually, it's much easier to use it on this one, where it's already factored for you. You use partial fractions, and then you kind of show telescoping, and then you get some expression for Sn, and then you take the limit, and that gives you the sum. So we all know that, so I'm not gonna do that again, if that's okay. But I'll show you another thing. We said that what if, and this was a common question in the tutorial, what if I don't see that it's telescoping, or I didn't think of using partial fractions because I haven't done that in like a year and a half. We've never been asked any questions like that. Or there's some other trick that I just don't see. Well, one thing we could do is we could start writing out these terms. So let's write them out. So what is S1? Remember, that's the sum of 3 over 3k plus 1, 3k minus 2, from k equals 1 up to 1, and then we have S2 and S3, and maybe we'll go up to, I'll write it over here, maybe we'll go up to S4. I don't know if we'll go up to S5. So we can see what S1 is. It's literally just where I sub in the value 1 into this expression. Let's draw a line here just to make things a little more clear. So what happens when I sub in 1? I get 3 times 1 plus 1 gives me 4. And then over here, I get 3 minus 2 is just 1. So I have 3 over 4. Okay? Okay, so then what is S2? It's just 3 over 4 plus whatever I get here when I sub in 2, okay? So that's 3 over 7 times 6 minus 2 is 4. Okay. Which equals 3 over 28. Okay. And then I need to multiply this, so I think I have 24 over 28. Did I make a mistake here? So we put in 2, we got 7. We put in 2, we got 4. Okay. Okay, so what's the next one? Sorry, I'm just checking over because it's going to go quite badly if we have an early mistake. So I think I'm not really seeing what I'm expecting to see. Okay, well, let's go with it. Sorry, this is not 7. Okay, all right. So then S3 is 24 over 28 plus 3 times 10, and 7. Okay, I'm just subbing in 3 into that expression. Just notice when I'm doing this, when I want to calculate S3, the sum of the first 3 terms, I don't keep recalculating all the other terms. Remember, S3 is literally just S2 plus the next term. Always do that. Like, you never want to be recalculating things you've already done. Okay. And we need common denominators here, so is this where I'm a little upset about this?
Right, 6 over 7.
I feel like I made a mistake here. Does anyone see this?
We can write here 6 over 7.
Oh, that's what's
Yeah.
sorry. Too long or too short of that. Okay, 6 over 7. Let's fix that. 6 over 7. All right, life's much better now. Okay, so then common denominator is much easier. I multiply this by 10, so I have 60 plus this, so I have 63 over 70. Okay, and that's gonna reduce down to 9 over 10. Okay, and then we could maybe calculate the last one if we want. It's not going to be too bad. So we have 9 over 10 plus, and then I just put in 4, 3 over 13 times 10. Okay, and that's going to equal. I need to multiply this by 13. Okay, maybe I don't want to do this. So it's 90 plus 27. So 117. You happy with that? Plus 3. So 120 over 130 equals 12 over 13. I don't know if that wasn't too bad. How do you multiply nasty numbers like that? Multiply by 10, multiply by 3, add them together. All right, so we see a pretty nice pattern happening, right? 3 over 4, 6 over 7, 9 over 10, 12 over 13. So our guess is that Sn equals to 3 times n over 3n plus 1. Okay? Could have said Sk, maybe that's a bit more appropriate. We've been using Ks. Okay? That's our guess. So let's prove it. How do you prove something like this? Your natural thing to use is induction. If you see another way to prove it for a particular problem, great, go for it. But induction is very, very natural to these series questions, because as we kind of saw when we were doing this manually, kind of the next term always depends on the last term. In an easy way, you literally just add on one more number. Okay, so use induction. Okay, base case. I just believe you can check that. We don't need to spend time on that. So induction hypothesis. Suppose Sn equals to, oops, all right, Sk equals to 3k over 3k plus 1. Okay, and now we want to show that that Sk plus 1 equals to 3k plus 1 over 3k plus 1, like this. Okay, so we just need to show that, assuming this, right? Okay, so let's do that quickly over here. Just check the time. All right. So what is Sk plus 1? By definition. Okay, so since we haven't used any assumptions yet, by definition it's equal to Sk plus the sum up to the first k terms plus the term, the k plus 1 term. So what's the k plus 1 term? It's just 3 over 3 k plus 1 setting in there. And 3k plus 1 minus 2. Okay? So then using the induction hypothesis, so maybe I'll write it here, induction hypothesis. We can say what this is, okay? And we know that it's just 3k over 3k plus 1, okay? And then we can simplify this one and say this is 3k plus 4 and 3k plus 1. Okay? Do we have it so far? Okay. So, we'll just find common denominator. Okay. So that is 3k times 3k plus 4 plus 3 over 3k plus 1, 3k plus 4. Okay. And at this point, you could also go over to this and plug in that formula and see if you can rearrange into each other, whatever method you want. You kind of know what you're doing. This is just kind of messy algebra now, right? Okay. But we can get to where we want to go to. We get 9k squared plus 12k. Yep. Plus 3. Okay. Over 3k plus 1, 3k plus 4. And that, I believe you can factor, I hope, let's see, into 3k, 3k.
Take out 1 factor 3.
We could do that, yeah. I wonder if it's best to do that first.
It's 1 and 4.
1 and 4?
Just guessing.
Well, we're going to need a 1 and 3, right?
Yeah, 1 and 3.
1 and 3?
Yeah.
I'm a little worried about that.
No, yeah.
Yeah, plus 1 plus 3. Oh, yeah. Oh, beautiful. I see it now. Thank you. Sorry, I was trying to look ahead. Okay. So that's nice. Things are canceling a bit. And you'll see now that we're basically done. Okay. So that's just equal to, we cancel the factors, and we have 3 times k plus 1 over, now we have 3k plus 4. I'm going to write that in a very specific way, 3 times k plus 1 plus 1. Okay, and that's exactly what we wanted to show. So you see, you can prove it by induction. This is quite different from probably what most of the tutors showed you in the tutorial. And this will help you with other problems where you may not get telescoping, for example. Just either don't see it or it's just literally not telescoping. So then what you do, try to figure out the formula and prove it with induction. So now to complete the problem, you know what we need to do. We need to take this limit. So we need to define the sum of the series. Okay? So we know that the sum of the series, and I'm just going to write a k for the interest of time. We know which series sequence we're talking about there. Is equal to the limit as k goes to infinity of that formula that we found for the partial sums. 3k over 3k
plus 1.
That's by definition. That's literally what we mean when we write the infinity up there. We mean you find the partial sums and you take the limit as it goes to infinity. And so what is this limit? Well, my favorite way, I saw people doing lots of different stuff. They do L'Hopital's and all kinds of stuff. My favorite way to do this is you just do this. 3 over 3 plus 1 over k. Divide by powers of k in the numerator and denominator, especially if you have some nasty long polynomial. Imagine you have a polynomial with like 15 terms. Like, I don't want to take the derivative of all those terms and do L'Hopital's rule, that's not nice. I'd rather just divide by the highest power of k, either in the numerator or the denominator, whatever makes it work. And then you take the limit as it goes to 0. This goes to 0, so you get 1. Okay? I should probably have a limit here. Yeah. All right, so let's move on. Let's see if we can, so we have about, probably spend a little bit long on this, but let's see if we can now do a lot of the other examples that we haven't seen using kind of like what we practiced here. And we won't have to prove the formulas and things, so, because in the next section we're just asked to show whether things diverge or converge. Just as a general rule, I mean, I think it made sense, but just for either for any of you guys or people who watch on the recording, what I meant here is you want to figure out that the power of k you divide by to make the denominator finite. That's the goal. You need that denominator to just be some number when you take the limit. If you know if the denominator is going to be 0 or something when you take the limit or the infinity or whatever, it's a problem. So you just find what's the power of k I need to divide by, and the numerator and the denominator to get the denominator to be finite. That's the goal. Okay. So do we have any special requests of problems from later in the tutorial, or shall I just pick some?
Yeah.
Yep.
So can you do this one? It's a sum, and k equals 1 is
With these roots. Okay, very good. So k over root k. Okay. Is that starting at k equals 1?
yes. I read it's not, so you can say 0, 1. So
There's the discrepancy.
that's all. So you check on it. I think it's second last.
This is a great example. Is that what it is?
Yes, so this is.
Oh.
We check maybe losing any effect.
Okay, so it looks like it's part n. Okay, so this is, I'll just write up here. Part n. Okay. So let's try to use what we talked about at the start in terms of estimating the overall order to just figure out that's going to give us a clue on how to do the comparison test. Okay, so again, everything's positive here. Like I said, everything on these tutorials is positive, so we can use the comparison test. And we see polynomials and roots and stuff. So that's a hint that we can just estimate the order of the numerator and the order of the denominator without too much work. If we had logs and exponents and stuff, we might have to think a little bit more, hopefully not too much, but in this case, we can just really immediately estimate the order. So order, and when I say order, I mean order as k goes large. So order of numerator, that's just 1. Order of denominator, well, you might ask me, what do I think of this as the order? Well, this polynomial inside of the square root has order 3, right? It's a cubic polynomial. And then if I just have this square root in front, I'm going to say that it's kind of like order 3 over 2. 3 over 2, like that. Okay? This is just me roughly thinking about how I think this thing kind of approximately behaves as k gets large. Okay, so the overall order, we're going to say that it's just minus numerator minus denominator. Okay. So that implies hints at me that this diverges. And I'm thinking that it's probably this is probably something that's bigger than the harmonic series, okay? Okay, I know the harmonic series diverges, and that has overall power to the -1, right? It's sum over 1 over n, or that's the harmonic series, it diverges. This thing is sort of sum over 1 over root n. So I think that it's even smaller, and so I think it diverges. Okay? Or sorry, I think it's even bigger, since root n is even smaller than n. Yeah. So let's just prove that. So guess diverges. Did I write that? Oh, I already wrote that. Guess, look for something smaller. Okay? Diverges with the comparison test means that I look for something smaller that diverges. Okay? So I need to make k over square root of k times k plus 1, k plus 2, smaller. Or I'm looking for something smaller than that diverges. Okay? So smaller means smaller numerator, bigger denominator. Okay? Okay. So what has a smaller numerator? Well, I could probably just get rid of 1. I could just do that. We'll see if we need it. What has a bigger denominator? Well, I can replace all the constants by just k. Okay? So for large k, you'll see what I mean by that. For large k, I'm just doing this. K plus k. K plus. You could write 2k if you were unsure, but you could just write k. That's fine. See how I did that? I took that one polynomial and just found something that's unambiguously bigger, and this is a very rough estimate, but it's going to be enough for us, hopefully. Okay, so what is this equal to? Actually, let's...
It's going to be equal to 4k squared.
To the 34 billion.
Sure, I'm actually worrying about that. I shouldn't have thrown away the numerator. Yeah, so...
2k times 2k.
4k squared.
Yeah, it's 4k.
Okay. So I actually want to do this. I'm going to keep my k. Okay. That was a bit silly for me to do that right away. Sometimes you get a little overboard. So that's going to equal to, I have 2k, 2k, so I have 4k squared times k is 4k cubed, right? So I have 4k cubed square root, okay? And what is that equal to? I don't know if we like the logic of this, but, well, I have a k to the 3 over 2, so I have some sort of constant, we won't worry about it too much, but 1 over root 4. And I have a 1 over 1 minus 3 over 2, which is exactly that order that we initially estimated, right? So that's just k. Do we agree? So if we do this cleverly, we should actually find something that has that order we estimated.
So like, if somehow you don't get this this order you estimated, then you know that, so maybe.
Well, if you get something smaller and the rules you use are correct, then it's fine. I think I was actually wrong here. Let's just check. We could have actually used a 1 here. I was just getting freaked out needlessly, I think. Is that right? No, is that wrong? We would have gotten 3 over 2.
Yeah.
It's not really what we're looking for. Yeah, so we were a bit too aggressive throwing it away. Okay, so yeah, what I would say to you is that's probably a good guideline for the kind of techniques that we're using. In almost all the cases, you'll feel pretty good if you find something that's of the order that you estimated already. If you could find something smaller than this somehow, with some special rule, like, that would be fine, right? As long as you find something, well, I say smaller than this, I mean something bigger than the harmonic series, but it obeys this sort of inequality, that's fine. This is a very rough estimate, but nonetheless, everything we've done is logically true. We just make this thing bigger, so we get this inequality. This diverges by P-series. Perhaps we can do one more. We have about 10 minutes. I think the more and more of these you do, the more and more you see how like kind of fluid it gets. We want to actually get to the point where we can kind of blow through this tutorial in like, say 15 minutes to half an hour. You just blow through, maybe not part 1, but part 2, we could blow through very quickly once we get to the tutorials. So do we have a suggestion for the next question? There's a recording, so, or I hope it worked out, so we had to change the setting on the recording. Do you have a suggestion for the next one, you guys? Yeah, like from the tutorial.
Yeah. There's another question where they check of 2 to the K was 3 to the K, and there's something like 2.
Okay, I'll take a look. Yeah, I've got it over here on the laptop today. Let's see.
Jamie, I got a copy.
Yeah, the copy.
Oh yeah, the copy. What was it? Because I'm not seeing the one you actually.
It's
There's something that are kind of simplified.
Yes.
Oh, that one. Okay, so k cubed plus 2 to the k over k squared plus 3 to the k. Oh, okay, so I see why that might.
Are we gonna have it every week?
Sorry?
Are we gonna have this chair every week? No.
I think all of the rest are going to be at Menzies again. I'll try to email earlier. There was a bit of confusion today because this venue was booked, but the recording was booked there, and I didn't know this was booked like a month ago. The recording was booked there recently, so I thought I didn't know. Yeah, so hopefully.
So this one is also booked for this session, but this one is much good because the chairs, you see.
Well, also I like having more.
Yeah, exactly. I
So
was gonna say that, so I thought maybe.
yeah,
This one is much cool.
yeah, it is better. So maybe I can talk to them about doing that. Yeah, I mean, I thought about saying that in the past, and then I thought, well, there tends to be quite a lot of admin with doing these
K
bookings.
cubed plus 2K.
K cubed plus, oh sorry, thanks. K cubed plus 2 to the k, k squared plus 3 to the k.
Yes.
Okay, very good.
Ooh.
Yeah, this one's going to be a little bit harder than just raw estimating, as I was saying, but that's all right. We can still work with it. So my rough impression, just looking at it, is well. Remember, exponentials are always growing faster than polynomials. Okay, eventually, like as soon as they grow very, very fast. So as soon as you have a k in the exponent, this number to the k, if it's greater than 1, obviously, sorry, if you have a half to the k, that's going to get very small very quickly. If you have 2 to the k, it's going to get very big very quickly. Okay? So that's the intuition here. So what we're thinking now is that the numerator as k gets large is going to be dominated by this term. That's kind of some language. Actually, physicists tend to use language like that, but it's also useful for as mathematicians to say this is going to be the thing that is significant. This is the thing that's going to be significant. These are going to matter less. Okay, and we'll try to show that. Okay, so we'll do our thing overall, or we'll say order of numerator, okay, and in this case, perhaps my notion of order of numerator is kind of not so useful. That we were talking about like powers of polynomials. Maybe what I should have said is dominant term, like something like that. But we could say that the order of the numerator is really kind of to the power k. I don't really want to introduce new notation and stuff. So let's actually say it this way. Sorry for your notes. Dominant term in the numerator is going to be 2 to the k as it gets large. As k gets large, dominant term in denominator, my handwriting is probably going quite badly here, is 3 to the k. Okay? So overall,
It's going to be 2 to the k minus.
well, we might just think of it this way, right? Yeah, see, I'm kind of breaking from our previous pattern. So it's a good question. It's a very good question. But you see the intuition is still the same. Overall, the dominant sort of thing, as k gets larger and larger and larger, the dominant sort of thing is actually going to look like a geometric series. And it's going to look like a convergent geometric series, right? Because this is less than 1.
That is okay.
Yeah. As k gets large, this number and this number really don't matter. If I put in 10 billion into this is a very big number, 10 billion cubed. However, 2 to the 10 billion is just astronomically larger. And if I put in 10 billion in here, 10 billion squared is a very big number, but 3 to the 10 billion is just astronomically larger. And I really challenge anyone who doesn't like trust that, because it's, I can just say it, but it might not be true. It's like, go check it. Put it on the computer or do it in the calculator. You'll see that this polynomial is nothing, and it doesn't even matter if it's a polynomial to the power 10. Like if it was k to the 10, it's still going to be insignificant eventually. Eventually, and actually very quickly. So something to the power k, as long as this something is greater than 1, is going to grow very, very, very fast. Okay, so overall, so we guess overall this converges. That's our suspicion. And why do we need to do that? Because we need to know whether we're looking for something bigger that converges or something smaller that diverges. So it's guiding us how to use the comparison. Okay. So our guess is we need to find something bigger. Okay. So we're just going to write down what we have, and we're going to look for something bigger. So we need to make the numerator bigger and the denominator smaller. So numerator bigger and the denominator smaller for this inequality to be true. So how do we make the numerator bigger? What's a really rough way to make the numerator bigger?
Just so you
Not to throw away. Numerator bigger.
Make that 2k.
Yeah, exactly. So we could have 2 to the k plus 2 to the k. See? Am I going to feel good about that? Yeah, I am. And then how am I going to make the denominator smaller? Just throw away k squared. Just throw it away. Just like we did with the other stuff. Throw away the thing you don't want. All right. So what do we get here? Not 2 equals 2 times 2 to the okay. Okay. Do you agree?
No.
So that's our thing we're going to compare with, right? This obviously converges as a series because it's a geometric series times some constant. Okay, so this converges. Okay, and that was our guess, right? That's a nice question. And I think next time we'll do a few more of these, but we'll also have some stuff from the next tutorial. And we need to start playing around with things that involve log and exponential. Sometimes we don't practice those.